welcome everyone. Today we have a special occasion at 1:30 when we finish this lunch. Everyone will step outside, we'll take a group photo. So the day is beautiful and very fitting. It will get very cold in the future, so we decided to do it today. So please join us after the meeting. We just heard an excellent ITC colloquium by Hummels from Caltech, and he will also give the first presentation here on some complementary aspects of what he described. We learned also that he has some hobby that is quite exceptional. Maybe you want to say a few words about that. But before we continue, let me just mention that we also have Pham from the University of Toronto. Oh, there. Good to see you. He will speak about polluting white dwarfs with Oort cloud comets. And then we hear from Vadim Semenov, our local colloquium organizer, who will tell us about how early did the Milky Way disk form. And there was a paper on the archive, I think, a few days ago, right? That he posted. So we had some preview of what you're about to describe. And then Zhuang from Caltech, over there. She will tell us about metals in star-forming galaxies, constraining multi-element abundances with Keck, KCWI. We start with the camera.
All right, thanks for hosting me, everybody. I'm Cameron. I'm primarily these days doing research on the circumgalactic medium, and forgive me for those of you who are in the colloquium. I'm going to repeat a couple of slides just to get everybody up to speed. So the circumgalactic medium, probably everybody, I don't know if everybody has familiarity with this. I'm kind of biased in my view. It's the low-density gas that kind of pervades the galactic halo and extends out and beyond the virial radius. It's fed by internal processes like galactic outflows from supernovae feedback and AGN and related sources, as well as externally from accretion from the cosmic web. So it's really crucial for understanding how galaxies evolve because it populates this reservoir around galaxies, but it's very, very difficult to observe. There's kind of a consensus picture for what it looks like based on some observations that we have of azimuthal asymmetry from outflows along the semi-minor axis and then accretion along the semi-major axis of galaxies. But there's a lot of questions that still remain about it in terms of what's the dominant origin of the material, what's the distribution of cool gas relative to hot gas in terms of the size of the structures, is it in thermal equilibrium, and most importantly, what transforms some galaxies into spirals or into ellipticals based on the flow or the quenching of gas through this medium into the star-forming portion of the galactic disk. As I mentioned, observations are really challenging for this because it's very, very low density, and so because density, the emission goes with the square of the particle density. And since it's so low, it's very low emission, low emissivity gas. We tend to see it in traditional means through absorption line spectroscopy, find a bright background source like a quasar, send a sight line through it, and then observe absorption features along that line of sight. Oops. The absorption features are specific to particular ions, and this is a phase diagram showing density on the x-axis, temperature on the y-axis. And so depending on the ion that's present, you can figure out something about the nature of the gas that you're probing and the absorption lines, if it's cold and dense, like these low ionization potential ions, or hot and diffuse and the high ionization potential ions. But what we'd really like to see is the light coming from the gas itself so that you could have some sort of spatial distribution and an idea of what's going on for the entire ensemble instead of just a single pencil beam sightline through disparate galaxies. So in simulations, we represent whatever we're simulating. In the case of this, a cosmological hydrodynamic simulation, we discretize that volume into different fluid elements, and then we represent that as a series of scalar fields or vector fields, in this case temperature or density in my cartoon. And we evolved those different, that fluid, accounting for hydrodynamics and gravity over time, and that puts together a movie something like this, where on the left side we're looking at gas density and projection, and on the right side we're looking at density-weighted temperature and projection, and you can follow the evolution of a system like, in this case, these are the fire simulations. This is a Milky Way mass system that's evolving from high redshift to redshift of 0, accreting galaxies over time, and with each accretion, you see cold gas gets turned into hot gas as you produce new generations of stars that generate outflows from supernovae and young stars that populate this low-density medium around the galaxy. But of course, we don't see the universe in density and temperature or other scalar fields. We see them in, as I mentioned, in particular ions. And so one of the tools that I've generated is for populating these simulations with post-processing to populate them with specific ions. It's this code called Trident that I put out a number of years ago and continue to support. So it consists of a lookup table made from hundreds of thousands of cloudy runs that give you an idea of what the ionization structure is based on density, temperature, and metallicity, and some assumed photoionizing spectrum that's redshift dependent. And then we can paint on the baryons and paint on the ion fields like neutral hydrogen or oxygen-6 and rerun that exact same movie, looking at neutral hydrogen or oxygen-6 in column density. And you can see very different behavior between these different ions relative to the scalar fields that we had initially. The neutral hydrogen following this cool filamentary gas, and the oxygen-6 sitting in hotter, more diffuse gas that really has is more isotropic and homogeneous. And then we can, again, because I'm working on synthetic models of this, and I'd like to make apples-to-apples comparison with observations, we can send sight lines through our simulation volume and produce absorption line features as it probes the various different structures in this. For this particular model, I've just arbitrarily chosen the silicon-2 1260 line, and as the sight line travels through this simulation volume, it encounters silicon-2 bearing gas with a certain line of sight relative to the observer, and you get absorption line features. And now the thing you're never supposed to do in a talk is give a live demo. So there's a code that I've been involved with called CosmoViz that you can go on the web and you can, oh shoot, see I'm already messing it up. The connection's not so strong, but you can interact with certain simulation volumes and then arbitrarily go into observe mode, arbitrarily place a sight line through, you choose your particular trajectory of that sight line, and then you can request a spectrum or request the skewer attributes. I like this skewer mode here. And what it's doing on the back end, there's an Amazon Web Services instance on the back end, and it'll be able to identify the sight line that we place through this simulation volume and then generate a spectrum on the fly. And it looks like it's trying. This is why you don't do live demos. And it'll be able to generate a spectrum on the fly, so that rather than just arbitrarily choosing your coordinates, you can actually interact with your environment and different simulations and send that sight line through appropriate structures that you might want to probe at different impact parameters and so on and so forth. And it's taking too long. So I'm going to go back to the presentation. In addition, as I said, what we'd like to be able to do is do this in emission, and there are narrowband photometry studies that do this, or IFU data now with MUSE or the Keck Cosmic Web Imager, which can find narrowband features and find the transitions in emission and find spatial resolution. So you could do this or with things like Dragonfly and other things that can pick up really low surface brightness gas. So Trident is in the work of being able to add these different capabilities to make emission maps for your favorite narrowband line transition, to be able to see what it looks in spatial resolution, to make predictions for what the Habitable Worlds Observatory or other upcoming IFUs will be able to see for this diffuse gas. And then finally, in a totally different vein, we can generate predictions for what fast radio burst observation should be able to see as well. So I've been talking about traditional methods by using ionization lines and so on and so forth. But fast radio bursts, based on the delay in the arrival of different radio signals, tells us something about the free electron content along that pencil beam line of sight. And so rather than a sight line with our absorption technique being able to tell you about absorption features, this just gives you a single dispersion measure value for that entire column from this distant, potentially cosmologically distant fast radio burst. And that number, that dispersion number, is the ensemble of the host's contribution, the cosmic contribution with intervening galaxies, as well as the Milky Way's contribution. And so we can make a similar map showing the dispersion measure and how it evolves over time for that exact same galaxy that we were looking at before. And you see that, to some degree, there's some evolution with the filamentary structure, and it's probing the dense gas, because if there's more dense gas, there's going to be more free electrons. But it gives us some insight as to how this sort of thing evolves. We can similarly make radial profiles of the dispersion measure, just as we were doing for different ions. And then we can make all-sky views from the contribution of the dispersion measure from our own Milky Way galaxy if we place ourselves inside of a simulation. So this is just one iteration of that from the fire simulations. But really the benefit of this, and I know Liam had a paper on this related to this in the last week that came out, it allows us to probe different computational models. This was a case of the fire simulations, which includes cosmic rays, whereas this is one that doesn't have cosmic rays. And you can see a very stark difference in the evolution of the free electron content for the Milky Way's contribution to the dispersion measure that may allow us, as we aggregate more numbers of these FRBs that are detected, oh, perfect. This is my last slide, to be able to constrain whether or not the cosmic rays or other physics feedback that are present in simulations are dominant or subdominant. Thank you. All right, I have 5 minutes for questions, right?
Speaking about the feedback.
Oh, I don't.
If you compare supernova-driven winds to AGN-driven winds, can you say something about the relative importance in matching data? Are AGNs important?
Are AGNs important for the circumgalactic medium?
Yes.
Yes, they absolutely are. They're driving huge outflows of material from the interior of the galaxy into this halo, oftentimes aligned on some sort of polar axis primarily. In terms of the simulations, I've done analyses on both the Tempest simulations, which are ENSO-based grid simulations, as well as the Fire 2 simulations. They don't have AGN that are present because it's hard to parameterize the behavior of AGN at these scales in these simulations. But the new Fire 3 models do have an AGN feedback prescription, so that's something that we'll increasingly look at. But I know that people in the TNG and the Eagles collaborations have their own prescription for how AGN behave, and certainly you get different behavior of the circumgalactic medium when you have those sort of systems that are present.
Okay. Any comments, questions? Please.
We might hear tomorrow whether the line emission mapper X-ray probe mission has been selected. And of course that would be looking at oxygen 7 and other higher X-ray lines. I wonder if you had looked at those predictions.
So I haven't done as much with X-rays. I am very excited to see the outcome of the probes. I was just told that the announcement happens today at 4 o'clock, which is very, yeah. That's what John Zhuyun, John's somewhere around here. That's what John told me. So very exciting. I myself don't look as much at the X-ray lines, but collaborators Emily Silich and John Zhuyun do a lot with this work. It certainly allows additional constraints to be made, both, really the way we're going to make progress in the field of understanding the circumgalactic medium is by taking, it's so hard and it's so elusive to pin down based on kind of the traditional measures. It's going to take new instruments like LEM or links to be able to really put constraints on a variety of different wavelengths. So when we have a mission in the UV by potentially Habitable Worlds Observatory, or Aspera is a new mission that's being launched next year that'll be looking at oxygen 6 lines in emission, as well as Sunyev Zoldovich, as well as FRBs. Really, I think the way forward is this kind of panchromatic view that we really need to incorporate all these constraints from various different sources.
That's the last question. Go ahead.
I was just curious if your webpage you were working on generated the skewer data.
Oh, that's a good question. Let's see, did it generate this? It didn't.
Oh, well.
Okay, yeah, so this is why you never do live demos, is because things go wrong. Anyway, thank you guys.
Before we let you sit,
Yeah.
can you summarize in 15 seconds your hobby?
Vadim embarrassed me by saying that I do silly things in the outdoors. He is correct. The thing that he was mentioning is I have the world record for the fastest kind of off-trail backpacking along the length of Death Valley from a few years ago. So it was unsupported, totally off-trail, just under 4 days, 170 miles of like hiking through the desert and drinking from questionable water sources along the way, and so there's actually there's an LA Times article about it, and it just reveals that I made a lot of mistakes in my life. So.
All right. Hi, so my name is Dang. I'm from the University of Toronto. There's no Death Valley there, so I can't really compete against that world record. I work with Professor Han O'Ryan. I'm on my 5th year of grad school. I'm presenting a paper that I published earlier this year, and hopefully I'll stay on the more interesting science side. If you are interested in dynamics, I'm more happy to talk about that with you afterward too. So this is what I'm not going to talk about. There won't be any of this. But if you are interested in something along the line of diffusive walk through a modified loss cone or angular momentum barriers, if any of those words sound interesting to you, I'm happy to answer questions or talk about it later. So the science question that I'm tackling in the last 5 years was that we see metals on old white dwarfs, atmospheres. And in fact, we see them between the white dwarf age from 1 billion years all the way up to 8 billion years old white dwarfs. This is very surprising because, well, you put a piece of metal on water, it should sink, right? And it's the same thing here. You have an atmosphere of hydrogen, not much is going on. You crash something into the atmosphere of the white dwarf, it should sink basically in a timescale of 10 to the 2 years at most. But we see white dwarf pollution, and it's at a pretty constant rate over the span of 8 billion years. It also spans a wide range of orders of magnitude in the accretion rate. So that's also an interesting problem to begin thinking about. There's also there's a rough cutoff here. That is just a detection limit right now. So there may be potentially even more white dwarfs polluted below this rate. So this is interesting because this is really the only way that we can actually probe the internal composition of planets outside our solar system, and even in our solar system, right? We do spectroscopy that only sees the surface. There are some recent missions to Saturn where they crashed the satellite into Juno, the satellite Juno into Saturn, and that was able to probe something about the internal composition of Saturn. But you crash a whole planet into a white dwarf or a comet, then you can actually start to disentangle what is inside these bodies just based on the spectra of polluted white dwarfs. But the problem is we don't actually know what are the potential reservoirs and how to deliver materials at a pretty constant rate to white dwarfs over 1 billion years. One proposed solution, and it's actually a pretty old solution, first proposed by Charles Alcock from 1986, and all the way up to now is Oort clouds. So the setup here is basically you have a star, the white dwarf, potentially have a companion, probably has a companion, and an Oort cloud object very far away. So before I talk more, the solar system Oort cloud is a reservoir of materials from about 5,000, 3,000 AU all the way to 100,000 AU. And it's formed by the ejection of planetesimals in the early solar system as they interact with giant planets. There are an estimate of about 10 to the 11 or 10 to the 12 objects in the solar system Oort cloud, and the total cloud mass is about 2 Earth mass. We don't know anything about white dwarf Oort clouds right now. So I will keep the number of objects and the total cloud mass as open parameter, but I will show later that it's actually very easy to, you can just plug any numbers here and my results will still scale linearly out. I also scale the 100,000 AU range. So the 100,000 AU there for the solar system Oort cloud is actually a very interesting number. It is the edge of the sun's Hill sphere. It is the edge of the sun's gravitational influence with the galaxy. You have any object beyond there, you will probably be lost due to the galaxy's gravity. So you scale it down because the white dwarf is less massive than the sun. And the last number, that gamma, is just the number density of Oort cloud objects. In the solar system, Oort cloud scales as a negative power law, which basically just means there's more object and you're close to us than far away. In the solar system, it's about 3.5. Also an interesting number. Also has deep dynamical reasons why. But for a white dwarf Oort cloud, I would just keep it as a general range between 2 to 4, just to probe what potentially the different structure can induce different pollution rate, for example. So in this work, we investigated the pollution rate of exo Oort clouds under the influence of galactic tide. So galactic tide is this mechanism where, as I mentioned, these Oort clouds objects are so far out, they're basically influenced by the gravity of the galaxy also. And this provides a torque to them, which allows them to migrate in eccentricity very quickly. This is actually the mechanism that allows you to bring something from, as I say, 10,000, 100,000 AU all the way to the tidal disruption radius of the white dwarf, which is only 1 solar radius. So this is a very efficient mechanism. It operates kind of like the Kozai leadoff mechanism that we're all familiar with. It exchanges eccentricity and inclination. So this is our first simulations results. The x-axis is just different Oort cloud structure. This is the number density gamma that I showed earlier. The y-axis on the left side just shows the number of comets accreted over a million years. And on the left-hand side, I assume that if that Oort cloud is like the solar system's Oort cloud, what would the number be? And we found that the accretion rate actually matches quite well with a lot of the accretion rate observed on white dwarfs. In the context of the observation, it spans this part of the observation by just purely assuming a solar system Oort cloud. If it has a companion, the dynamics gets a lot more interesting, which is what I mentioned at the start. But just purely from simulation result, which is the blue curve here, you can see that having a planetary mass companion reduced the pollution rate by 1 order of magnitude. So now we're down to 10 to the 7 gram per second at various different Oort cloud structure. And if your companion is a star, like if a white dwarf binary or a white dwarf main sequence, then this pollution rate will be reduced to under the current detection limit. Some people might ask, well, would you have an Oort cloud if your star is 1,000 AU? I don't know, that's a different research paper. But as far as we have considered in this paper, if a companion is less than 100 AU, it could still potentially form an Oort cloud, but those pollution won't be observed on white dwarfs. So in the context of observation, this is what we currently have. By just purely assuming a solar system Oort cloud, we can actually produce quite a large range of parameters spanning several orders of magnitude as observed by observations. And the other key important component is that people see pollution constantly over billion-year timescales. Can this do that? To do this, we developed simulations that are capable of resolving the number of comets hitting a white dwarf over time. And we found that if you have a companion, this pollution rate is decreased by a factor of 2, factor of 3 over a billion years. And if it has no companion, then pollution rate is pretty constant. All of this matches the observations pretty well. And I mentioned we developed new simulation methodology. This was able to simulate 10 to the 8 objects with 3 bodies, a comet, a planet, and a white dwarf with galactic tide. And it took only 48 cores over 2 days. To compare with previous results, people have been able to do 5,000 comets before my paper. And to do this, partly I had to break the code that my advisor wrote, which was not a good day. But there are now solutions for that, which is published in another paper. I mentioned earlier we don't know anything about Oort clouds around other stars. So that's why a lot of the numbers I put earlier assumed the solar system Oort cloud. But say if you found that Oort clouds around other stars are 10 times heavier than ours, you can just plug that number in there and everything should still scale linearly out. And this gives a nice and beautiful scalable problem. Now I'm going to discuss a few things. This is not about carbon-oxygen white dwarf. I'm curious, I'm just jealous of observers sometimes that they can make up acronyms. So this is mine. Just going to talk about some common reasons why people might object to this solution. One is, can an Oort cloud even survive stellar evolution? The white dwarf typically can experience a natal kick when it's born. It's on the order of about 1 kilometer per second. Oort clouds, comets, have orbital velocity on the order of 1 kilometer per second. So if a star gets a kick, this might eject the planet, eject the comet. There's a paper before mine, and they found that about 90% of the Oort cloud is ejected by the kick of the star, which is a potential problem until you remember that 10%, which is what we have left, 10% of 10 to the 11 is 10 to the 10, and my results scaled linearly, so everything just moved down a little bit, and we can still explain about 2.5 orders of magnitude in this diagram. Another concern is that when we look at spectra of white dwarfs, we don't see volatiles, which is a telltale signs of comets, for example. One, it's actually not true. We do see polluted white dwarfs with volatiles. They are just much more rare. 2 is that Oort clouds do not have to be icy. The ones we have in our solar system is icy because, well, Jupiter was outside the ice line, so it kicks off all the planetesimals that are icy. But if Jupiter was inside the ice line, then this would have kicked all the rocky planetesimals, and then you would have a rocky white dwarf. I'm just going to skip all of that and just go to my conclusion slide in respect of the time.
First, if the star loses more than half of its mass, then any bound object will become unbound.
Yes.
And you didn't mention that. But
yes.
The second point is we do see, at least in several systems, a planet being disrupted tidally by
yes.
the white dwarf. So that could be a reservoir
yes.
that far exceeds because it's so close to the white dwarf.
Yes. So this plot, they also accounted for the mass loss. So it did account for the mass loss of the star and the kick by the star. 2, planets will be a great reservoir. My concern with them, though, is you crash one planet in, it makes a disk, maybe it lasts 10 million years. You will have to crash about like 80 or 800 planets to constantly pollute over 8 billion years. So I think planets are potentially a problem there. It might be a good solution for young white dwarfs. So, yeah.
So it looked like in your model that if there was a star orbiting around the white dwarf, that there'd be very low pollution rates.
Mm-hmm.
We know white dwarfs live around stars, so
yep.
we actually can you test that? You're basically predicting that there would not be much pollution for white dwarfs around companion stars.
So yes, I am, and that would be a nice step forward in observations to actually start to correlate white dwarf binaries and pollution. Unfortunately, I don't think there's much known about that right now. A lot of polluted white dwarfs all the polluted white dwarfs we know are in the solar neighborhood within 100 parsec. So we just basically need more samples and more binary white dwarfs, and yeah.
So we've got good reason to believe that stars, including the sun, were born in much denser environments and were ejected as the first cluster fell to pieces. So what impact does this have? Because if you have an Oort cloud in that very dense environment, it's much more vulnerable to scattering.
Yeah, I know that people do consider the sun's birth cluster when they simulate Oort clouds, and the Oort cloud basically gets depleted over time. So over, I think, 10 billion years, the sun gets depleted by a factor of 10 or 100. Like the Oort cloud's mass is depleted over time. But I'm not sure if there's any work right now on Oort clouds at various galactic environment and over different stellar masses. So I think that's also a new interesting research direction to go for.
Could you say again, what's the time scale for that? I mean, you basically see it's very constant accretion rate.
Yes.
Billion-year time scale. What sets that?
It's the galactic tide. Galactic tide time scale is 300 million years, and basically you have duty cycles of these things. And
Okay.
yeah.
So it's that percentage.
Another thing you didn't mention is the envelope of the star. When it becomes a white dwarf, the envelope spreads, and it
Yep.
could produce new rocks around the white dwarf, and that's a much larger reservoir, at least 0.4 solar mass.
0.4 solar mass, absolutely, yeah. So I think that's also an interesting point, that can this envelope re-accrete? As far as I know, I'm not too sure if that can do it. We see these envelopes spread out very far, and then they just kind of dissipate into space. But yeah, that's an interesting point.
Okay. No. Oh, there is a question there. Go ahead.
Now, this might be an obvious question, because I don't know too much about white dwarfs, but you're assuming that the white dwarf is not convective at all?
The white dwarf atmosphere is not convective. People do convections inside the core, but I think on the surface, it's all just a layer of
So
gas.
does the metal sink
Yep.
into the core?
The core does core things, and people do interesting core simulations, but on the surface, it's very boring,
So they're
unfortunately.
not going to be dredged back up?
Unfortunately.
The
not.
surface gravity is very large, so diffusion is straightforward. Thank you so much.
Thank you.
Yes, there. Okay, awesome. Hello, everyone. I'm Vadim Semenov. I'm an ITC fellow here, and I'll tell you some new insights about the early evolution of the Milky Way, and more generally about the galaxy formation in the early universe, based on some new simulations that I've been working on recently. You may have heard that with JWST there was a revolution in this whole field. It's too intense? Okay. How's it now? Great, thank you. So one of the things that we learned is that there's a lot of galaxies at this early times, much more than we expected before, and there was a range of reactions from the theorist side following these discoveries, from very extreme claims like the whole lambda CDM is wrong, to more mild corrections like maybe the star formation in the early universe is more bursty, or there are non-trivial variations in dust properties or IMF at these early galaxies, or maybe stellar feedback is not as efficient in these galaxies as we think. Apart from this large abundance of early galaxies, another related discovery was that the disk galaxies are also very abundant at early times. This is very different from the previous picture, where it was believed that disk galaxies like our Milky Way form relatively recently at around redshift 1 or 2, which is motivated by the rest frame UV view of the high redshift universe with Hubble and ground-based IFU instruments, which is highly biased to actually star-forming environments. But now with JWST, we see these galaxies in rest frame optical. Earlier with ALMA, we had access to ISM kinematics at this high redshifts, and it became clear that these galaxies are in fact ubiquitous in this, at this high redshifts. So it means that these can form much earlier than we thought. Now closer to home, we can map these discoveries to the timeline of our own galaxy evolution, as now can be probed in the local data and local distributions of chemistry and kinematics of stars in the Milky Way, as was shown in this plot by our esteemed Vadim Chandra. He's somewhere here, I think. And he showed this plot a few months ago in this meetings. But what it shows is the orbital circularity of stars is a function of metallicity, and metallicity can be thought as a proxy for the formation time. So this dynamically hot component, like spheroidal distribution of stars at low metallicity, is thought to reflect this very early phase of evolution before any disk was in place. So during this epoch of when first galaxies were formed, it is now can be probed by JWST. And then at high metallicities, we see stars piling up in this top part of this distribution, reflecting the formation in nice star-forming disks, like typical star-forming galaxies today. And in the same data, we can see this sharp transition that reflects the formation of the Milky Way disk. And in the Milky Way, this transition, this disk spin-up happens unusually early, which is kind of reminiscent of this abundant disk galaxies in the early universe. Also can reflect unusual mass assembly history of the Milky Way. So for example, in cosmological simulations like TNG, there's roughly 10% of Milky Way mass disk galaxies that form disks as early as the Milky Way. And in fact, we were able to find one that resembles Milky Way very closely. So this one is from the TNG simulation. So the results that I'll show you is are simulations that are designed to probe into this regime and tell us more about this epoch of disk formation at early times and what is going on there. So how galaxies form disks and switch from this early bursty formation to disk galaxies that we see today. To this end, we took this galaxy from TNG and resimulated it with more detailed ISM physics. So here, this new simulations at the top, and for comparison, the original TNG model is in the bottom. So there are a few differences. So it's a different code. It's somewhat high resolution, but most importantly, it's the physics that goes in. So it's cooling down to low temperatures, on the flat radiative transfer coupled with the gas thermodynamics, and more detailed modeling for star formation and feedback that I'll talk a bit later. But what is clear is that when we include all these new features and model the same initial conditions, then the properties of gas on small scales are qualitatively different. We form a lot of dense, cold structures that are completely missing in other models because of the way how the dense gas is modeled in this large-scale cosmological simulations. And as a result of this, the differences in star formation history are also quite dramatic. So here, for example, here's the comparison of the stellar mass and star formation rate. So this new simulation, which I'll call Oort after the code that I'm using, shows significantly more early, more efficient, and more bursty star formation than the TNG model. So star formation ramps up exponentially early on, and then saturates settles. And this transition at around redshift 7 corresponds to the formation of the thin, relatively thin, stable star-forming gas disk. And again, just a reminder, so this is not a typical Milky Way mass galaxy. This galaxy represents one of the early forming disk galaxies from TNG simulations, but in TNG it happens at redshift 3, while with this more detailed ISM and star formation physics, disks can form much earlier, at around redshift 6 or 7. And at this point, the properties of this early stellar disk are very similar to the properties of the low metallicity population of Milky Way stars, which you can ask me later. And also, this galaxy, it looks very similar to this early disks that we see with ALMA, and now there's new data coming from JWST on the kinematics of early galaxies. But what it means is that at least some of these early disks can be progenitors of Milky Way-like systems. And the really cool thing that we can do in these simulations is that we can tell what's going on small scales. We can make predictions about the star formation on the scales of individual star-forming regions because the way how star formation is modeled in the simulation. So star formation is often in simulations parameterized with this so-called star formation efficiency per free fall time, which is also motivated by how it's also measured in observations. And observationally, it's measured to be of the order of 1% per free fall time, and typical giant molecular clouds in the Milky Way and nearby galaxies. And simulations often treat this as a parameter. So you assume some value, you can tune its value to get the observables that you want. But at the same time, the theory of star formation in the turbulent interstellar medium tells us that the value of this efficiency per free-fall time is a strong function of the properties of supersonic turbulence in the interstellar medium, such as a viral parameter or Mach number of turbulence. But the problem is that it's not trivial to account for these variations in galaxy simulations because this requires knowledge of turbulence on parsec and subparsec scales in galaxy scale simulations, which cannot be done self-consistently. So the way how I'm doing this is by adopting this class of methods that allow us to explicitly model turbulence on unresolved scales using these methods that are developed in a completely different field of modeling terrestrial turbulent flows, like in aerospace engineering, climate models. And again, this is something that is almost never done in the context of galaxy simulations. But what it allows us to do, it allows us to predict what the turbulent state of gas is on unresolved scales. And then we can couple it with these models of star formation in turbulent ISM and forward model star formation efficiency in these early galaxies. So in principle, this model can give you any value of the efficiency in the galaxy at these early times. But interestingly, when we look at the average values, which are shown here, we get values close to 1%, very similar to what is observed in the local universe. So on small scales, the star forming regions, in terms of the star formation efficiency per free-fall time, they're similar to the local universe. And we have some idea of what's going on there. So here's another work by a student at the University of Chicago, Eva Paulsen, where we're looking at this using more idealized simulations of a dwarf galaxy with the same star formation feedback physics, but it's isolated dwarf with the metallicity varied in a controlled fashion down to 1% solar. And despite of huge variations in the structure of the ISM, the star formation rates, amount of cold gas, the average star formation efficiency per free-fall time locally is close to 1%. And the reason is that it's an efficient regulation, local regulation of star formation by feedback that quickly destroys the regions that become too efficient. And in the end, it settles into a narrow range of efficiency of a few percent, regardless of large-scale environments, because turbulence decay doesn't depend on these properties. Okay, awesome. And I have just the last slide where I want to tell the main conclusion, where apart from this close to 1% efficiency, there's also a huge variation. And this variation, in fact, sets the scatter, short-term scatter and star formation rate. And the scatter, so here it's expressed in terms of UV variability, and its total variation, which is shown here by the black line, is in fact consistent with what is needed to explain this early UV bright GWC galaxies. And again, just to clarify, so this scatter is dominated by these variations in the local star formation efficiency, which is very different source of burstiness of star formation from what people usually talk about in simulations, because this is a stochastic variations in the properties of turbulence in the ISM that's make these small scale variations that can result in these transitions between different regimes. So as opposed to more vigorous variations of the total mass content or gas densities in these galaxies that result in destruction of the disk in usual cosmological simulations. So yeah, and I'll just leave my takeaways and connect it back to the picture of the Milky Way. Yeah, thank you.
Just to clarify a pedagogical point, stars always form in a disk because you need low temperatures to make them, right? So it's always a thing. But this jump that you see is because of the last major merger, the circle, that basically removed the disk shape of the stars that formed before that. And so, I mean, we are in a few billion years, we collide with Andromeda, and then the picture will be completely different because everything will go down again to low circularity. So the point is, it's really the time since the last major merger that you're measuring, right?
That can be one of the things, but these galaxies at these early times, they are too not massive enough to develop disks. So this is how the galaxy looks like at this time. So at this point, yeah, the process like star formation that disturb the gas that tries to settle into the disk, they prevent gas from settling into the disk. So disk doesn't actually exist in the Milky Way before this formation. But for some galaxies, yeah, for many of the galaxies that experienced the major merger, this transition will reflect the timing of the last major merger. But this didn't, for the Milky Way, there's evidence that this didn't happen because the total mass of stuff in this non-disky component is close to the mass threshold at which galaxies tend to start forming disks.
What you're saying is there are molecular clouds that are not in a planar configuration. They're sort of moving around in the halo.
What? No, I'm talking about this low metallicity population.
So you are making stars not in a disk configuration.
Yes.
In those early times.
Yes.
Molecular clouds not sitting in a plane.
That's right. And so the star formation, it's very different. Yeah, so the density is so much higher. So it's turbulence in the whole halo, right? So you can form stars anywhere, and not necessarily in molecular gas because the formation time of molecular gas are very long. So in fact, we find that most of the star formation here happens directly from the neutral gas before it has enough time to fully be converted to molecular.
Okay, that can be tested in observation. Questions? Looks like everything was clear, Vadim. Thank you so much.
Okay, so hello everyone. My name is Zhuyun. I am a final year PhD candidate at Caltech, primarily working with Chuck Seidel and Evan Kirby on the chemical evolution of galaxies. So in this talk, I'm just going to present a small observing program I designed on Keck Cosmic Web Imager, or KCWI, as part of my thesis research. And as you can tell, I'm not really good at coming up with the acronym for my program, so it's just like really straightforward. So these program targets are very nearby galaxies, mainly star forming roughly between 10 to the 8 to 10 to the 10 solar masses, and we basically acquire optical IFU data on Keck to characterize their chemical abundance, both in stellar population and ionized gas to great details. Okay, so just as a recap, since I'm going to talk about the chemical abundance, for my talk, I'm not going to talk about the total metallicity, which is basically all the heavy elements on this periodic table, but instead, for me, as an observer, metallicity always means single element abundance. So we have the gas phase metallicity as the oxygen abundance in the interstellar medium, and we also have the stellar phase metallicity measured as the iron. But for my cases, since I'm very curious about the connections between the metal in different phases, it turns out that it's a little bit complicated to really interpret the relation between the stellar and gas metallicity, because the two elements were just formed by very different processes with very different formation timescales. So these comparisons kind of similar to comparing a fresh apple with an old banana and trying to really understand the time evolution of the apple. So that's definitely not ideal. So that's why we actually want to borrow the old apple, the magnesium in the stars, because magnesium is another alpha element. So similar to oxygen, they were both produced by core collapse supernovae with very short formation time. In this case, we always expect the magnesium atlas to track oxygen much more closely. So in this talk, I'm just going to focus on the measurements of these three elements: gas phase oxygen, stellar magnesium, and stellar iron. And now the next question is, how can we observe these low mass galaxies? Because these galaxies are always very faint, so usually they look really puffy on the images. In this case, it's probably not ideal to observe them with either fiber or slit spectrograph, because they are just not really large enough. In this case, we basically just miss most of the light from the outskirts. And ideally, we wanted to collect as many photons as possible. And that's why we decided to observe these galaxies on the Keck Cosmic Web Imager, the KCWI, because we can not only cover the entire galaxies, but also get both spectral and spatial information at the same time. So it's just kind of like a bonus. So in the past few years, I've been working on leading this observing campaign to get the galaxies between 10 to the 8 to 10 to the 10 solar masses on the Keck Cosmic Web Imager. So far, we've already finished this program because I need to graduate. So there are 59 galaxies in total. We lost 2 nights, but still quite a big, decent sample size. So as you can see in this plot, all the colorful data points are the galaxies in our sample, while the background gray dots are just the galaxies at a similar redshift from Sloan as a reference. So you can see most of the galaxies in our sample are still highly star forming and actually fall on this star forming main sequence. Although I do have 2 quiescent galaxies I just observed for fun, kind of like the filler for the night. And why this very particular mass range? It is really motivated by my previous work where we seems to actually find something interesting in the stellar mass, stellar metallicity relation measured as the iron abundance. So here you can see that there's like a big jump between the low mass MZR shown by the blue line and the high mass MZR shown by the green line. So we are just curious about what really happens at this mass. But if you are familiar with all the, most of the existing spectroscopy surveys, you may know that we don't have a lot of coverage for galaxies below 10 to the 9 solar masses, mostly because they are just very faint. And the spectrum for these dwarf galaxies are not really decent enough to yield reliable stellar abundance measurements. And that's why we thought maybe it's not a bad idea to observe the Keck, and that's really how I started this project. And in this talk, I'm just going to focus on the global abundance measurements, even though this is still an IFU data. This is really because for now, we want to maximize the data quality and trying to figure out what would be the best way to do such abundance measurements. For the gas phase oxygen abundance, it's quite straightforward. We'll just make use of the Strong-like calibrations from the empirical relation derived from the H2 regions. But for the measurements of the iron and magnesium abundance, it's much more complicated. So it turns out that with all the existing stellar population synthesis model, we just cannot derive magnesium and iron in star-forming galaxies directly by feeding the entire spectrum. So we really have to come up with a new method, which we call the two-step method. And again, I'm not really good at coming up with a name. But because of the time limit, I'm just not going to talk too much details here, but feel free to check the paper if you are interested in the method. But you can, this is just one spectrum of, one integrated spectrum of the galaxy in our sample. I actually plot them on the log scale so they can see all the small features much more easily. But overall, this is a really incredible data set that really allows us to do these abundance measurements. So here I show the comparison of the metal abundances in different phases. On the left here, this is the comparison between the stellar and gas metallicity. So the stellar Z versus gas Z you may have already seen in the previous literature. While on the right, I show the comparison, probably the first ever comparison, at least to my knowledge. Please correct me if I'm wrong. Basically the comparison between the alpha element in different phases. So we have the gas phase oxygen versus the stellar phase magnesium. And the black dashed line in each panel shows the 1-to-1 ratio indicating the solar abundance pattern. So you can see that when we compare the two panels, magnesium indeed tracks oxygen much more closely, not only in terms to the absolute values, because they are like definitely closer to the black dashed line, but we also see a tighter correlation between the magnesium and oxygen. So this just like really proves what I said earlier, magnesium might be a better element to be compared with oxygen. So it's really time to think about whether we can do these detailed abundance measurements in star-forming galaxies and just add another dimension for us to really interpret the galactic chemical evolution. Another thing I want to point out is that most of the galaxies in our sample have higher oxygen abundance. This is very interesting because oxygen is kind of like the chemical enrichment of massive stars that just form out of these ISM. While on the other hand, magnesium, measured from the rest frame optical, reflect the chemical enrichment of lower mass stars that form at an earlier epoch. So the axis in, the oxygen probably suggests that the star formation of the galaxies in our sample is probably built on the wild mass ISM. In other words, the external accretion from the metal pore gas, from the surrounding environment is not the major power source sustaining the star formation. And of course, we are interested in the mass metallicity relation, since that's really like the initial motivation for this project. And we want to know what is the shape of the stellar MZR for our sample, and also how other things, whether the relation has like some secondary dependence. It is very well known that in the current universe, the gas phase metallicity, MZR measures the oxygen abundance, show a secondary dependence on the star formation rate. So galaxies with higher star formation rate tend to be much more metal poor because of higher gas fraction. But it is much more controversial for the stellar MZR. We know all the galaxies, whether they are forming stars or not, found on this one universal stellar MZR, while we do see a much larger scatter in the MZR of massive galaxies. And many work have actually suggest these might be related to the changes in the star formation rate. So we want to know what would be the case for our sample. And that's how we constructed the stellar MZRs, not only for iron, but also for magnesium. So in these plots, all the rectangles with gray color arrow bars are the star-forming galaxies in our sample. I also have these two dots showing the quiescent galaxy as a reference. And also to make a fair comparison, we actually remeasure the stellar abundances of both iron and magnesium using the exactly same method for a sample of massive galaxies. So basically, the takeaway here is that we do see a larger scatter in the stellar MZR of star-forming galaxies. And when we really look at the color bar, so basically all the star-forming galaxies are color-coded by the specific star formation rate, we do see that galaxies with higher specific star formation rate tend to be more metal poor at a given stellar masses. And this effect becomes more clear when we look at the lower mass end. And this again just says that starvation is probably really working here. So when the galaxy is on their way to be quiescent, they become more and more chemically evolved because star formation is really eating the existing ISM, and eventually the galaxy just die. And finally, I just want to emphasize that even though what I'm presenting here is based on the global abundance, eventually the goal of this project is really just to examine the spatial resolved properties because we know these galaxies host as stars form at different epochs, and we believe this might be a way to help us better understand the evolutionary history within the galaxy. Thank you.